it states that a compound that is positively charged is more acidic than a neutral compound. Let's look at the example below to understand this fully. So let's take a look at the conjugate base of this acid over here. As we can see, it results in a conjugate base with a negative charge. Then let's take a look at the conjugate base of this acid. We can see that it's neutral. So, one key thing to understand here is that this is more stable than the original form, than the original acid. And this is less stable. So this has a negative charge, and the original acid has no charge. Therefore, it is moving to a less stable state. And we know in chemistry, or organic chemistry in general, compounds are always attempting to achieve stability. Therefore, if the resulting state is unfavored or less stable than the original state, it's less likely that the transition will occur. Here we have a positive charge, and we're moving to a neutral compound. Therefore, we will move towards it at a faster rate, and the compound will be more acidic than a neutrally charged compound. As for our second rule, electron delocalization. The conjugate base with more resonance structures has a more acidic acid. Let's take a look at the example to understand this fully. So by taking a look at the conjugate base resulting from this acid, we can see that we're going to have a negative charge on the oxygen. The same is true for this one. However, there's one key difference. With this compound, we have a resonance structure. When the double bond moves down from the nitrogen down to the oxygen, we'll have a resonance structure. And compounds with resonance structures are more stable than compounds without resonance structures. Therefore, this base over here is more stable than this one. This also applies when we have more than two resonance structures. So if we were to have three compounds over here, and one of them had more resonance structures than this one, then it would also be more acidic than this one. So we'd have compound X greater than the double bond NOH, which is greater than the O and the H. But our third rule, bond strength, states that as we go down the group, the bond strength decreases, therefore the H is released more readily. What does this mean? Well, the theory behind this is that as we go down a group, the electron radius gets bigger and bigger. And what this means is that there's a weaker interaction between the atom and the hydrogen. So let's take sulfur, for example, and oxygen. So oxygen has a smaller electron radius than sulfur. Therefore, when a hydrogen comes to bond with the oxygen, the two nuclei will be closer to each other than if a hydrogen came to bond with a sulfur, because the electron radius is larger, therefore the interaction will be weaker. This means that when the bond strength decreases or the electron radius increases down a group, the hydrogen will be more likely to be released and the bond strength will be weaker, therefore it will be broken easily. So we can see here that this means that this compound is more acidic than this one because the sulfur has a larger electron radius than oxygen. Moving on to the fourth, electronegativity. As electronegativity increases, acidity increases. What does this mean? Well, the theory behind this is that as an atom gets more and more electronegative, it's more likely to take electrons from the hydrogen. Therefore, when comparing an oxygen and a nitrogen, for example, oxygen being more electronegative than nitrogen is more likely to take the electron from the hydrogen and release the hydrogen than nitrogen is because it is more electronegative. Therefore, in the example shown here to the left, oxygen, the compound with oxygen bonded to the hydrogen would be more acidic than the compound with nitrogen bonded to the hydrogen. So finally, we have the fifth rule, which is the inductive effect. It sounds scary, but it's actually the easiest rule we've done so far. It states that the more surrounding electron withdrawing groups we have, the higher the acidity. So, we know that fluorine is an electronegative atom. Therefore, it acts as an electron withdrawing group. What it's going to do is it's going to hold the electrons closer towards it and cause what we call a partial positive charge on the carbon. This is going to cause the carbon to pull electrons away from oxygen in retaliation in order to maintain its stability, therefore causing the oxygen to also have a partial positive charge. This will make the oxygen more electron hungry. Therefore, it's going to be more likely to take the electron from the bond between it and the hydrogen and release the hydrogen. Therefore, this compound over here is more acidic than this compound over here. This also applies to even more distant groups, as we can see here in this bonus point. So this compound is more acidic than this compound, which is more acidic than this compound. This is because we can see it getting further and further away from the acidic hydrogen, as this was on the first carbon, this is on the second carbon, and this is on the third carbon. Therefore, the further away it is, the weaker the inductive effect is. And this also applies when there's more than one inductive group. If we were to have two fluorines, it would be more acidic than if we had one fluorine. So one point to remember is that rules 3 and 4 apply to the atom directly connected to the hydrogen, while rule 5 applies to distant groups. So before we move on to problem solving, we need to keep some points in mind. These rules only apply to weak acids, not strong acids like HCl or H2SO4. When we have HCl or H2SO4, we can't apply these rules, and they're instantly the strongest acids present in the problem. Your professor will never ask you to differentiate between two strong acids without a pKa value, so we don't need to know how to differentiate between two strong acids. And one thing to keep in mind is that the stronger the acid, the weaker its conjugate base. Now keep these in mind for the problem solving we're going to be doing next. Moving on to problem solving. Our first question asks, which of the following is the strongest acid? So we have fairly identical compounds with one minor change. The only change is the halogen group. Now, since the halogen group is a distant group and it is an electron withdrawing group, the first thing we should think about is the inductive effect. In organic chemistry, most of the time when we have an electron withdrawing group, it's most likely going to be a halogen because that's what we use most of the time. So, now that we know the inductive effect is what we should look at, how do we know which one of these is the most electronegative? Is the most acidic. So, as we know, the inductive effect relies on the electron withdrawing group. So, the more electronegative an atom is, the more electron withdrawing it is, the higher electron withdrawing capability it has. So as electron withdrawing capability goes up, acidity will go up. As you mentioned above, this is because this causes a cascade of partial positive charges, where a partial positive charge is imposed on this carbon, and it causes a partial positive charge on this carbon, which causes a partial positive charge on the oxygen, and makes it more likely to take the electron and release the hydrogen. So which one of these is most acidic? Now, we know that fluorine, chlorine, bromine, and iodine are all in the same group. Therefore, going down the group, electronegativity decreases. And by that logic, fluorine is the most acidic, or the most electronegative. Therefore, the compound yielding the fluorine is going to be the most acidic. The answer for this question is going to be this one. And obviously, if we wanted to arrange them, it would be in this format. So our second problem states, in which of the following reactions does equilibrium favor the reactants? So this is a question professors like to bring a lot on the exam. So what we need to do to understand it is look at what the question means. So in which of the following reactions does the equilibrium favor the reactants? Now, here we have acids and bases on either side of the reaction. So this is the reactant side, and we need to find out in which one of these does the reaction favor moving towards the reactants. Let's do that. So first we'll start with A by drawing the molecules. We have CH3CH2OH, and we have NH2 minus because Na is a spectator ion. And then we have CH3CH2O minus because Na is a spectator ion, and NH3. Now, on this side, this is the acid and this is the base on the left side. And on this side, this is the base and this is the acid. So in order to know which side is favored, we need to look at which side has the stronger acid and which side has the stronger base. And we need to take the opposite side, because the side with the stronger acid is more likely to release its hydrogen, producing something on the other side, right? So we have an OH here. It's more like it's a stronger acid than NH3 because oxygen is more electronegative. Therefore, the O is more likely to release its hydrogen, becoming O minus, and the NH2 is more likely to accept that hydrogen than release it, forming NH3. Therefore, in this equation, the product side is favored. So this isn't the answer. In our second one, we have CH3, CO2, and OH minus. And on the bottom and on the right side we have CH3, CO2 minus and H2O. Now we can see that this is our base, this is our acid, this is our base, and this is our acid. So to understand the equilibrium here, we should look at our acids and our bases. So CH3CO2H is connected to the H is connected to an oxygen, and there's a neighboring oxygen causing an inductive effect. So that is two things increasing the acidity. However, in H2O, we don't have many things increasing the acidity, as the O is bonded to a hydrogen on its own without any neighboring stabilizing carbons or any inductive effect. Therefore, this acid is stronger than this acid, and OH minus is a strong base. Therefore, we don't even need to look at the other base, and we can know that it is a stronger base than this base. So here we have a stronger base. On the left side we have our stronger base, and we have our stronger acid. Okay, my bad. And on this one we have our weaker acid. I flipped them again. And our weaker base. So, as we said, we're going to favor the side where the stronger base and the stronger acid were able to get what they wanted and release their hydrogen and accept the hydrogen. Therefore, this side is what's going to be favored here. Because the stronger acid got what it wanted, it released its hydrogen and got a minus charge, and the stronger base got what it wanted and it got the hydrogen. When we have primary carbons, the electronegativity increases. So primary carbons are less acidic than OH, but they're more acidic than NH. Why is that? So when we have a primary carbon, we have, well, it's sp hybridized. And that means we have 50% S character, which means that the electrons are all closer to the nucleus. Therefore, the bond between the carbon and the hydrogen is going to be weaker because of bond strength. Now, we're just going to have to memorize this point, sadly, because there's no way to logically deduce it. So we just have to memorize that primary carbons are in between nitrogen and in between oxygen. This is very important. Okay, moving on to part C and D. So let's draw the atoms or the compounds that are reacting. OH minus because Na is a spectator ion. C triple bond C with a negative charge. Draw the hydrogens here. Plus H2O. And over here we have C triple bond C with an H's. Plus NH2 minus. And C triple bond C minus plus NH3. Now, going back to our rule, primary carbons are more acidic than nitrogen, but less acidic than oxygen. So, over here, we have our weaker acid, because as we mentioned, OH is more acidic than primary carbon H. So here, H2O is more acidic than C triple bond CH. So this is a stronger acid. Here we have C triple bond C minus. Now, since the acid is a weaker acid than H2O, as we mentioned earlier, the stronger the acid, the weaker the base. So the weaker the acid, the stronger the base. It works in both ways. So C triple bond C minus is going to be a stronger acid, a stronger base. And OH minus is going to be the weaker base. Usually, as I mentioned before, OH minus is the strongest base. However, in cases like this, where H2O is more acidic than the acid, the stronger base is going to be the one resulting from the weaker acid. So here, in part C, the reaction actually favors the reactants. This is because the stronger base and the stronger acid both get what they want. The acid releases its hydrogen and the base accepts the hydrogen. Therefore, it'll produce the reactant side. Now, let's explain part D real quick. It works in the same way. However, as we mentioned, the C triple bond C is a stronger acid than nitrogen. Therefore, here we're going to have the stronger acid on this side. And we're going to have the stronger base on this side. Therefore, to get what they want, they're going to push the reaction towards the products and not towards the reactants. Okay guys, thanks for watching. I hope this helped. If you want to see anything I didn't cover in this video or would like me to cover a different topic, leave a comment down below. I also left a Google Drive link and an email in the description with the ACS review problems I used in this video. And you can also shoot me an email if you have any questions or anything you'd like to be clarified.